Hey guys, what's up? Welcome to another video of CHE 101, and today we will be talking about reactor design for multiple reactions, specifically for parallel reactions. So we will use still the same set of equations and formulas, but this time we will add formulas for parallel reactions, specifically in backmix reactors. So we have here the instantaneous fractional yield, small letter phi. So the expression is phi of R over A is equal to the rate of formation of R all over the rate of decomposition of A. So this simply means that the fraction of A that has reacted that turned into R on a basis of one reactor only. And then we have the overall fractional yield, capital letter phi. So the expression is phi of R over A n, where n here represents the number of reactors, equal to CRN minus CRO all over CAO minus CAN. And it's equal to this long expression. So the overall fractional yield tells us the same thing, except that the basis now is the entire reactor system. So if we're going to illustrate that, so this is the reactor system. So the entering concentration here are, let's say, CAO and CRO. And then here would be CAO, CA1 and CR1. Here is CA2, CR2, and so on. And then at this point, let's say this is CAN minus 1, CRN minus 1, and then this is CAN and CRN. So to show you the difference between the two yields, instantaneous fractional yield will refer to the fraction of A that reacted that has turned into R per reactor. So we can say that this is the instantaneous fractional yield at reactor 1, this is at reactor 2, and this is at reactor N. While the overall fractional yield is the fractional yield of the entire system. So capital Phi represents this whole system. Okay? And then to simplify this long equation, this is simply equal to, okay, let's write it here, 1 over CAO minus CAN times, this is CAO minus CA1 times the phi of R over A at 1. So I'll just shorten that to phi of 1 plus CA1 minus CA2 phi of 2 plus until CAN minus 1, the final reactor, minus CAN phi of n. Okay. So we will use these equations later when dealing with the problem, right? So now let's move to the problem. So liquid substance A produces RNS in the following parallel reaction. The feed enters two backmix reactors in series with tau1 equal to 2.5 minutes and tau2 equal to 10 minutes. And initially, we only have 1 mole per liter of A fed into the reactor system. So we need to find the composition exiting the second reactor. So to illustrate first the problem, we have two backmix reactors in series. Okay. So we have here CAO, which is equal to 1 mole per liter, and you don't have anything else. So we proceed to the second stream. So we have here CA1, CR1, and CS1, and finally CA2, CR2, and CS2. Okay, and we also know that the rate of R is equal to CA squared moles per liter per minute, and then R sub S is the same. R sub S is 0.2 C sub A moles per liter per minute. And then remember writing rate loss. So the rate of the composition of A should be equal to the sum of these two. Okay. Going back to the reaction, A participates in both reactions. So both rate loss should be present for A. Okay. And then we have the first reactor to have a space time of 2.5 minutes, and then the second one has 10 minutes. Okay. So let's try to solve first using the fractional yield method. So how do you go about it? If you remember the expression earlier, we only need the concentrations of A. So let's solve first for the concentrations of A. So for the first reactor, we have T sub 1 equal to CaO minus Ca1 all over negative R sub A1. So this is 2.5 equal to 1 minus Ca1 all over Ca1 squared plus 0.2 Ca1. And you should get Ca1 equal to 0.4 moles per liter. And then for the second reactor, so that's Ca1 minus Ca2 all over negative R A2. So this is 10 equal to 0.4 minus Ca2 all over Ca2 squared plus 0.2 Ca2. And you should get here Ca2 equal to 0.1 moles per liter. Okay. Now, let's use the formula earlier. So we know that the instantaneous fraction, the overall fractional yield rather, is equal to 1 over CaO minus CaN. In this case, we have two reactors, so we write 2 times CaO minus Ca1, small letter phi of 1 plus Ca1 minus Ca2, small letter phi of 2. But what are these values? Let's solve first for phi of R over A and phi of S over A. So phi of R over A is just the rate of R over negative rate of A. So that's Ca squared all over Ca squared plus 0.2 Ca. Or let's simplify this to Ca over Ca plus 0.2. Using the same method, you should get phi of S over A equal to 0.2 over Ca plus 0.2. Now, to solve for the final concentration of R, remember that the overall fractional yield is also equal to CRN, so CR2 minus CRO all over CaO minus CAN or Ca2. So basically, these two, the denominators will cancel, and then we have CRO equal to 0. So we can express CR2 as CaO minus Ca1 times the phi of 1 here, okay, plus Ca1 minus Ca2 times the phi of 2. And the phi of 1 is equal to Ca1 all over Ca1 plus 0.2. Okay, so let's write that down. And then similarly, for phi of 2, that's Ca1 minus Ca2 times Ca2 all over Ca2 plus 0.2. So substituting values, we have CaO equal to 1 rather, 1 mole per liter. So 1 minus 0.4 for Ca1 times 0.4 all over 0.4 plus 0.2 plus here Ca1 is 0.4 minus Ca2 is 0.1 times 0.1 or Ca2 all over 0.1 plus 0.2. And simplifying this, you should get 0.5 moles per liter of CR2. Okay. For CS2, I won't write the full detailed solution, but we will use the same formula. But this time, the phi of 1 should be now equal to 0.2 over Ca plus 0.2 since that's the phi of S over A. So I'll just write the working equation for this one. And then I leave the verifying part to you. All right. Ca1 minus Ca2. Ca2 plus 0.2. You should get here 0.4 moles per liter. And to check, okay, our Ca1 is, our CA2 is 0.1 moles per liter. So if we add the three, CA2, CR2, and CS2, the total is still 1 mole per liter. So that means that the solution is correct. I'll present another way of solving this. So basically, we will just use the formula for the space-time. So for the space-time of 1, this is equal to CAO minus CA1 all over negative R sub A, which is equal to CR1 minus CRO all over R sub R. And this is also equal to CS1 minus CSO all over R sub S. Similarly, for T sub 2 or tau sub 2, this should equal CA1, since CA1 is the entering concentration, minus CA2 all over negative R sub A. Let's put 1 here. Let's put 2 here. Okay, then this is equal to CR2 minus CR1 all over R sub R2. And this is also equal to CS2 minus CS1 all over R sub S2. Now, let's solve first for the one or after the first reactor. So 2.4a for CA1, we have 2.5 equals 1 minus CA1 all over CA1 squared plus 0.2 CA1. So this should give you CA1 again equal to 0.4. And then for CR1, we have 2.5 equal to CR1 minus 0 all over, we have CA1 squared, so that's 0.4 squared. And this should give you CR1 equal to 0.4. Lastly, CS1, 2.5 equals CS1 minus CS0, so that's 0, all over 0.2 times CA1. So that's 0.2 times 0.4. And this should give you CS1 equal to 0.2. Okay. I leave the computation for the second backmix reactor to you, and you should get the following values. So CA2 should be equal to 0.1, CR2 is equal to 0.5, and CS2 is equal to 0.4. So the answers match with the ones earlier. Okay, and if you total the concentrations, they're still equal to 1 mole per liter. And that's how you know that the solutions are correct, the solutions and the answers. Okay, so that's it for this video. So in this video, we learned how to solve problems involving parallel reactions in a series of backmix reactors. So thank you guys for watching, and I hope you learned something from this video.